Hi, everyone. Today we're going to look at this lovely Sigmund 21 paper, Don't Look Back, Look into the Future, Prescient Data Partitioning and Migration for Deterministic Database Systems. So this paper, based on the title, obviously talks about data partitioning, data migration, in deterministic systems. So in particular, it talks about the dynamic data partitioning or repartitioning and dynamic data migration. And the reason why we want to do these things, look at the data dynamically and repartition it or migrate it, is to optimize the transaction performance. So this particular paper looks at the deterministic databases, which were inspired by the Calvin system, this deterministic distributed databases, that is. In a Calvin-like database architecture, we have client applications that can submit the transactions to their local sequencers. Right? So that sequencer A will receive the request from the client. And what sequencers do is they kind of batch the transactions and assign them some order. Right? So the entire idea of a sequencer of this deterministic database is to kind of pre-order the transactions before they go into the execution, so that we kind of avoid a lot of the contention by having this pre-ordering happening, right? So we don't have to figure out the order of transactions on the fly. And this allows us to, this allows a lot of benefits in terms of transaction execution, since they're pre-ordered. We can optimize things like have the independent transactions run concurrently. Dependent transactions acquire local locks instead of distributed locks, just by the virtue of this pre-ordering. So after the sequencers will create this batch of transactions, and each sequencer will forward the batch to the local scheduler, right? And the scheduler is essentially going to pass these transactions into the execution layer. And there are a few options that can happen, a few things that can happen here. If the transaction is purely local, meaning it only accesses the data that is hosted in this particular partition, then the transaction can just execute against the local storage, right, against the local data. Now, if the transaction involves the data that may be hosted by other partitions, then there is this additional step that will involve, like this transaction may need to read the data from other partitions, right? So this additional step shown here as D is this like extra coordination that is involved in distributed transactions in deterministic databases. Now, this creates a bit of a problem for us, because now we have a system that kind of has two performance modes for transactions, the fast local transactions and slow distributed ones, right? Distributed transactions, they need more time because of this cross-partition communication, as they need to fetch the data from other partitions. And of course, this may delay other transactions because of the locks that this distributed transactions may hold. So the paper actually talks about this kind of performance modes a little bit more in details. It describes things like, goes back into history and describes things like what can happen if we have these horribly slow transactions, and how much the performance of deterministic systems will deteriorate if we have some slow transactions somewhere in the past. So yeah, that's kind of the model of deterministic databases, and these two performance modes. It's a big problem. So ideally, we want to get rid of this slow performance mode, right? Ideally, we want to speed up the transactions so that we're not slowed down by these distributed transactions having to go across partitions, fetch the data, and have more cost of coordination. So if we somehow can magically get rid of these distributed transactions, or at least reduce the number of distributed transactions, then we'll make the entire system in general faster, right? So the question is then, how can we get rid of these distributed transactions? And this is not a new problem, really. The option one would be to look at the historical access patterns. Obviously we have a system, it's been operating for some time. If we look at these historical patterns, then we can see which data is accessed together frequently, and then we can repartition the system to collocate these frequently accessed pieces of data together, so that going forward, these transactions that were used to be distributed now most likely going to be local, because we collocate the frequently used data. So obviously this works really well when we have a steady kind of workload, the workload that doesn't change its access patterns too frequently and too drastically, right? So if we can slowly learn and maybe slowly adjust based on this learned locality from the past historical data, and that works great. So the second option is to essentially consolidate the data in one place only when it's needed, right? So if we have a distributed transaction, we may decide to say, okay, instead of making it distributed, let's put all this data for this transaction on one machine, on one partition rather. So we consolidate the data, we run a transaction locally, and we hope that this is not like a fluke transaction, right? We hope that because we consolidated this data, this kind of pattern will persist into the future, right? So we adjust quickly right away for the first transaction, and hope that this locality that we created by consolidating the data is going to persist. The system described in this paper, Hermes, it essentially tries to solve the same problem. It tries to solve the problem of reducing the number of distributed transactions. However, it makes its life a little bit more complicated, because it says, well, what if we don't have a very predictable workload, right? What if the workload in our system can change quickly? Well, that will be a problem for option one, and that will be a problem for option two, quite frankly, because then we create a lot of fluctuations and data movement that may not be necessary, right? So rapidly changing workloads create a problem for the existing solutions that try to minimize the amount of distributed transactions. So how can we solve this, right? So if we look at this historical data, if it's no longer a predictor of what's going to be in the future, then it's not a good use for us. So Hermes solves this dynamic data partitioning by not looking at the historical data, but kind of looking at the current data in a system. In particular, because we're working with these deterministic systems that batch the transactions, Hermes look at the transaction itself, a transaction batch rather. Right, so in a batch, we may have multiple transactions. I show an example here on the screen. So I have 8 transactions, and I have this 3 partitions distributed system. Right, so partition 1 has objects A and B, partition 2 has C and F, partition 3 has object Z, and we have these transactions. Like some of them, transaction 1 only reads A, transaction 2 will read A and write A, so is transaction 3. Right, so they can kind of all go into this partition 1. Transaction 4, it needs to read A, which is in partition 1, and write to C, which is in partition 2. So this is a distributed transaction. Actually, I think I meant to write B here. I think I messed up on the example a little bit, but let's carry on. So if we try to put these transactions, like all of the transactions we have, to their partitions, we'll end up with partition 1 having these 3 transactions, A. We will send the transactions that, let's say, access partition, like these 3 transactions will access partition 2, and a few of them, like transaction 5 and 8 in this case, will read B, write to C, so they are distributed transactions, so they will have to fetch the data from partition 1. So even though we send it to partition 2, it kind of depends on the partition 1 to supply the data. And these transactions 6 and 7, they read F, which is in partition 2, write to D in partition 3. So again, they create this distributed transaction pattern here, right? So this pattern, this slowdown, is something we want to avoid. So naturally, we can start to think, what Hermes is actually doing is it will try to relocate the data and reshuffle the transactions between the partitions. So we can move the data object C from partition 2 to partition 1. And with that, we actually can move all of the transactions that used to read B and write C to the partition 1, because now it will have both objects B and C, right? So we moved the data, we moved all of these transactions, and now we have all of these transactions local, right? So in the base case, the object B had to move twice, so we had 2 kind of distributed transactions. Now object C just moves 1, right? So we saved 1 distributed cross-partition interaction by moving this object and moving the transactions that depend on it from partition 2 to partition 1. So this is kind of the net benefit, right? 1 fewer distributed interaction. And the same happens with the object F. We can move it to partition 3, and then these transactions become local. So instead of having 2 distributed interactions here, we again reduce it down to 1 distributed interaction. So that's kind of the nutshell idea of dynamic data partitioning that Hermes is proposing based on the batch, right? And of course, ideally, the next batch will have similar access patterns, but if it doesn't have similar access patterns, then we can again rebalance it and take advantage of the locality as quickly as possible and for as many transactions as possible. So, however, we can see that in my example, this kind of dynamic data partitioning may actually not be very good for us. Right? We moved all the data from partition 2 away, and we moved all the transactions from partition 2. So we create a major disbalance in the workload here, right? We put a lot more work on it.
Can I ask a question?
Yeah.
At what point does the read and write become take up more time rather than sending the entire object C or F? Because it's kind of if C and F are small enough or big enough, different things would be best, right?
Yeah. So yeah, obviously this is a kind of a simplified example, right? But okay, let's go back here, right? So for now, let's assume that the size of this object is about the same, right? So if the size of the object is about the same in this simplified example, then essentially we have to read B twice. So we kind of move B twice for each of
I see. Yeah.
Right?
So reading is equivalent to just moving the object itself?
Well, again, if we have a simple objects, right, the key value, right? Then reading a key value, reading this value is kind of equivalent to moving it. It involves the same operation, right? Reading from one partition, transferring this data over network. The difference is what do we use this data for? Do we use it in the transaction itself, or do we store it now in new partition? Right. So
Oh yeah.
in
Okay.
terms of resources, under the assumption that these objects are about the same size, in terms of resources, now we can cut down number of movements, right?
Yeah.
From having 2 reads, and most importantly, 2 cross-partition moves, we can cut down to just 1 cross-partition move, for the relocation of the object.
Yeah, and then like the writes are simple too.
Yeah.
Okay.
So
Yeah.
obviously, this will crumble if, in my example here, if object C is, I don't know, 3 times the size of object B, right? Then you may actually end up wasting more resources than by making this move. But for the sake of simplicity in the example, we kind of assume that they're about the same. In real life, you can account for these differences, right?
Okay, yeah, thank you. That's all.
Okay, awesome. So yeah, that's kind of the basic idea of Hermes, right? To try to move the objects based on the patterns that it observes in the current batch instead of the patterns observed historically, right? By observing the current batch before the batch is executed, before the batch starts to execute, Hermes can kind of preemptively move this data, then execute the batch with the best locality. So there is still data movement, there is still cost, but the benefit is kind of twofold, right? Here, I did save 1 extra move, and second is if the same workload continues, right? If the workload pattern doesn't change, then I again kind of prepared myself for the future, right? So the future read B, write C transaction will not have any movements whatsoever, right? So if the workload is the same, then this locality will persist, and we can keep gaining the benefit into the future batches. But yeah, as I was saying, doing this kind of naively may not be a good idea because we create disbalance in a system in terms of how much data each partition stores and how much work each partition needs to do, right? So in my example here, partition A has like 6 out of 8 transactions, partition 1, and partition 2 has no data and no transactions. So the second part of Hermes is actually trying to optimize for the load balancing, right? So it says that once we have this like optimal locality optimized plan, right, on how to move the data and how to move transactions, we can start thinking about load balancing, right? So maybe the best locality is not so great for the load balancing, so we can maybe make the locality a little bit worse for the sake of load balancing. So what Hermes will do is, for the sake of load balancing, it may decide to add more distributed interaction for a particular batch, right? So here we cut down 2 interactions, but if we add 1 more interaction and actually move object A to partition 2, then we can also have all the transactions, which supposedly relatively small compared to the object size. We can move them again to partition 2, and now we can run all of these transactions that involve A in this partition. These transactions BC that were distributed before now become local after 1 move, and F and D doesn't change. So and it can do it like Hermes can do this in kind of a few iterations and come up with this hopefully more or less balanced strategy on how to repartition the data for a particular transaction. So this is more like a plan, right? So it comes up with this plan, then executes this plan by moving the data, moving transactions, and then starts running kind of regular transaction protocol in deterministic Calvin-like systems. That's kind of the protocol in a nutshell. Now I do want to talk about the the evaluation and a few points that were interesting to me, right? So traditional systems, clay, I don't know why it says CLAP. I think it's supposed to be clay. That's the one they compared. Clay is the system that moves the data based on the historical patterns, right? So it doesn't require like heavy batching. It actually doesn't rely on the batch size to learn this locality patterns. Hermes does rely on the batch size to learn the locality patterns. So in my expectation, Hermes would need bigger batches, which may increase the latency. However, they claim that the latency of Hermes system is actually much better than the latency of the system that uses the historical data and doesn't rely on the batch size to get the good data. So that was a little bit surprising to me. I was expecting bigger batches for the system to work well, to provide good throughput, and bigger batches would most likely mean higher latency, but that's not the case here. On the batch size itself, the authors run the experiment and they do show that when the batches are very small, right? When you have like 10 transactions in a batch, you don't get as much gain as much performance gain as when the batches are bigger, right? So by increasing the batch size, again, kind of intuitively, you're capturing more of the locality patterns in a given batch, so you can do more locality shifts and optimizations within the batch. So because you're not relying on the historical data, it kind of makes sense that the performance does improve as the batch size gets bigger, so you have more data to infer these locality patterns. The bigger chunk of their evaluation was comparing their system, Hermes, with, let's say, Clay, right, which is this historical system. This is a system that uses the historical data. And for that, they use this, they compare it in terms of throughput, and they use this Google workload, the way they describe it, complex Google workload. However, I do have questions in terms of how reasonable this workload is. Like they use this workload because it's very unpredictable. But I tried to follow the reference that they give for this Google workload, and it's a workload from a Google Borg cluster. So Borg is the scheduling system. It's not a database. So they say that they took these traces from Google and they converted them into a database workload. So I'm not sure how realistic this is in all of the examples, all of the scenarios, like how general this is, to take the trace from a scheduling system and make it into a database workload. Nevertheless, when you do have this unpredictable workload, looking at the historical data, so Clay is this kind of blue line that is very faded, like on the background. It doesn't help you much. Like if your workload patterns are like more or less random, then the historical data, learning from the historical data doesn't help you much. And learning quickly, probably shouldn't say learning, adapting quickly based on the batch before you execute the batch gives you a little bit more performance because you can optimize within the batch already, right? So you don't have to wait for the data to become historical data before this optimization takes effect. Here you optimize before you run the batch. So as soon as you run this batch, hopefully you're going to get some improvements right away. So this allows for greater workload fluctuations while still keeping the optimizations. And that's kind of supported by a different workload that they run. The throughput is the hotspot. And I personally think this may be a better workload to show, the differences between the practical differences rather between the system like Clay and Hermes. So we can see that at some points, they do perform about the same, like in terms of throughput. But these dashed lines, they introduce the change in the hotspot, right? So that's kind of like a big change in the access locality. And Hermes can adapt very quickly, right? So like here, it's very simple, very small degradation here, almost no degradation here because it adapts on a per batch basis. Adapts before it can run the batch that has the new change. Versus Clay, the historical, the system driven by the historical data, it kind of has to, it gets the batch and it runs it against the data, against the historical placement that no longer matches the new placement of data, right? The hotspots. So it will take it some time to adjust. Okay, that's kind of what I have for this paper.